Yeah, maybe I need to write atoms continuum.
Will you ever get a PhD?
I don't think I have the time to, because PhD is like full-time study.
Is it school? I don't know.
Yeah.
PhD,
Yeah, full-time study, 9 to 5.
like school.
Like school, yeah. For like 4 years. Do you know?
No, it's not full time.
No, it's full-time.
And then exams?
Hmm?
And then exams, and then?
Some exams, but mostly research-based.
And you have to make a research.
Yes, exactly.
You also teach during your PhD.
For limited hours, like 5 hours maybe. It's not enough money. Do you know what I mean?
No, my sister has one.
Where though?
Who?
But medicine is totally different. Totally different. Because when you're doing medicine, they can give you like internships and work experience and work placement and full-time work. That's not the same for non-medicine. Totally different.
And how long does the master take?
1 year, full-time.
Engineering.
Mm-hmm. Yeah. Okay. Oh, then I have another meeting and I want it to be Easter. Right. DIFC. Where's Mir, by the way? Has anybody seen him? I think we're on.
I think we'll come some more.
Have we only done one lesson on atoms, or have we done 2?
We did the decay.
That's all, right?
Yeah.
Yeah, okay, so we're on to the next lesson. Great. Great. What? What's going on? What's going on? Oh, yeah, okay. Hey. Hi. Okay, here we go. Radioactive decay equations. Sorry, did you get that? You got it? Good stuff. Right. Whoops, sorry. So there's uranium-238. This material is radioactive, so it releases alpha, beta, and gamma radiation. So uranium is a good example of a radioactive material. But how can we detect this radiation? So how can we measure this radiation? Well, problem with measuring radiation coming off of something like uranium is, in fact, radiation is colorless, so you can't see it. You can't see radiation. Odorless, which means you can't smell it. Tasteless, which you shouldn't do because it'll kill you, but you can't taste it. And chemically inert, meaning it won't react with other materials. So it's very important we know how to detect radiation because it's so dangerous. But if it's colorless, odorless, tasteless, and chemically inert, how do we find it? Because it could be in this room right now, killing us slowly, and we wouldn't know it until we're dead. But how can we know it's in this room if we can't see it, smell it, or taste it? Now, before continuing, these are important properties of radiation, that they are colourless, odourless, tasteless and inert. And it's something you should make note of.
The uranium.
Not just uranium, all radiation, all alpha, beta, gamma radiation.
Radiation
Characteristics, yes. Or just properties. Got that, guys? Yes, Adnan, yeah? Okay. So, before going on to how we can detect it, we need some definitions. So we have this concept called activity, which is a bit like speed, in that it's a rate, and it's a rate of decay, and basically it's how many unstable nuclei decay in a second. So if, for example, the activity was 1 destruction per second, it means in a second 1 nucleus of uranium-238 is destroyed through radiation. So this is the definition which you will need for the exam.
Do I need to write the between brackets?
No. Continue?
So about the point?
Don't need that. Okay, so the unit we measure activity in is the becquerel, or BQ. And it's an SI unit. And the definition is quite simple. 1 BQ is 1 destruction of a nucleus per second. That's all it is. In other words, when 1 nucleus is destroyed due to radioactive decay per second, we say the activity is 1 becquerel. Got that? Did Iyad go home sick or something?
Yeah.
Where's home now for Iyad? Did he move?
No.
Alright. How come he was on campus over the weekend? Wasn't he? Are you sure?
He was in...
Because Monday morning I saw him at 9 o'clock, he said he stayed the night.
Yeah, he was in Saturday. No, Sunday. He came Sunday night from night.
Ah.
So that they can do that.
Sleepover.
Yeah, essay.
Yes, what is it? Huh? Do what?
To do the essay.
Oh, essay sleepover. That's not fun. Essay for what? That's definitely not fun. Alright, now do you have this? Okay. So, notation. A represents activity and the units are BQ. So for example, what would this mean? A equals 5 kilo BQ. What would that mean? 5 kilo BQ.
5,000 nucleus are being
Disintegrated per second. Yeah. N, we use N to represent the number of atoms. For example, 10 to the 6 atoms. And sometimes we're a little bit careless with the A. What I mean by that is really A is a negative number. But just like with acceleration, we can drop the minus if we use the right words. For example, if I say the activity rate for destruction of atoms is 5 kilo equals, then really maybe we should say the activity is minus 5,000 because you're losing 5,000 per second instead of gaining 5,000 per second. But when we talk about radiation, we are always losing atoms. So the context, a bit like with acceleration, when you say deceleration, you know it's slowing down. So we don't have to worry too much about the minus in the answer. If you want to play it safe in the exam, you could just say 5,000 kilo equals, and then in brackets you could write lost or destruction or whatever like that. Calculating N is not too difficult. You learned how to do that in materials and in chemistry. Using the PV equals N or T is one way, but just if you knew the number of moles, you could do it that way. For example, 12 grams of carbon will have how many atoms?
12 over 16.
Yeah. Is it Avogadro's number, isn't it, Joe? Just the definition. Yeah. That's right, isn't it? Yeah, 12 grams of carbon will have that many atoms of carbon. Okay, so just before going on, you might just want to make note of the letters A and N and what they represent. A for activity, N for number of atoms. And just make some note about the minus sign, please. Continue? Oh, great. So this is how you can detect radiation using something called a Geiger-Müller counter, or often just called a Geiger counter. You might have seen these on TV before. They make a clicking sound when they detect radiation. Do you know? Yes, kind of like this. Yeah. So how do these Geiger-Müller counters work? Let's have a look at the diagram, which you'll need to draw. So before you draw that, I'll explain here. What? No. Okay. So what you have here is you have your radiation that comes in through this mica window here. Now mica is kind of like a glass, but I believe it's very fragile. You know, it's very delicate. So it won't let the air in, but it will let the radiation in. Do you know what I mean? Now, unlike glass, it will easily break. I'm sure if you drop this, it will be broken. Why does it need to be so delicate? Well, remember we said when we did the penetration, I think we said a piece of paper could stop an alpha particle, didn't we? Like your hand can stop alpha. So we can't use glass here because then, for example, the alpha radiation won't get in. So we have some gas in here, I don't remember what gas it is. I think it's maybe something like helium? Is it? I don't remember. But anyways, whatever gas is in here, when the radiation comes in, it ionizes the gas. Ionization is something you do in chemistry. So the energy from the radiation ionizes the gas. So the electron is freed, and we're left here with a negative electron and a positive ion. Then also what you have here, this is called the cathode, which just means the positive, and this is called the anode, which just means the negative. And here we have an electric field because we have a voltage here of 5,000 volts. Oh, I'm sorry, cathode is negative, anode is positive. So we have an electric field in here. So because there's an electric field and the particle has a charge, it will move in the electric field using the formula F equals QE. Remember that? When we did fields? So now what will happen is the freed ion will move down to the cathode, which is negative because this is positive, and the electron, which is negative, will move to the anode, which is positive, and you'll have a change in the current. This counter can pick up the change in the current, and then it will know that some radiation came into the window. So it's actually quite a simple machine. It will work for detecting alpha, beta, and gamma, but I don't know if it's best for beta, because it is still a little bit difficult for the alpha to get in through the window, I'd imagine. The beta will have an easier time getting through, and the gamma will have no trouble.
But alpha wouldn't cause that much damage.
No, alpha will not penetrate so easily. But the good news is the alpha is not as dangerous to your health as beta, because your clothes would be nearly a good enough protection against alpha radiation. It's only dangerous to you if it gets inside of you. If you have a cut or something like this on your skin, you know. So this is how the Geiger counter works. Important vocabulary which you need to write down is the word cathode and anode. These are not words I've given you yet. Cathode just means a negative plate, and anode just means a positive plate. Did we do it in batteries, these words, cathode and anode? No, maybe we do. It doesn't matter. You can write it down again anyway. Oh, you have it in chemistry? Yeah, okay. But you heard these words before. That's great. Can you draw this carefully in your notebook?
What is that?
This?
No.
I don't know what this is. I don't know why that's there. I don't know. Go away. What is this garbage? I'll have to reopen it. What was your question, Sharif?
I'm sorry.
Okay.
So all of that can be
Cathode? Anode?
in your side. Some sort of radiation.
Ionization. Ionizing radiation. You know this word ionizing from chemistry? Yeah, ionizing. Ionizing radiation.
And the one with microwindow.
Microwindow. Anode. Cathode, atom, ion, electron, counter. Yeah? Make it beautiful.
Mike.
Yeah, micro. Not the same as micro.
Micro, the car.
Yes. Nissan micro window, yes.
There's a name there.
Yeah.
Okay.
But I tell you what,
Okay, so
just draw a rectangle. Just look at it from the side. Just draw a rectangle. Got that, guys? Okay.
Should we write the steps?
What do you mean?
So
Oh, like what I said? No, I just... If the picture's enough for you, then the picture's enough for you. I was just explaining how it works.
And the exam.
In the exam! Do you know? Let me have a look at the learning outcomes just to start here. I don't think so for the exam. You definitely need to know the name of it, because I could easily imagine a question that says, I'm picturing something like, give the properties of radiation that makes it difficult to detect. And then part 2 could be, what instrument could be used to detect radiation? And maybe part 3 could be to draw it. But I don't think they'll have you explain it too.
what's the name? Geiger.
Geiger counter. Now, what I can picture though, however, is them giving you this diagram and maybe asking you to name the parts of it, possibly. I don't think they will, but something that's much more likely is they give you this diagram and they ask you to calculate things like the electric field strength. So what would you need to know to calculate the electric field strength here?
Resistance.
Nope.
FQ and F.
Nope. Not this. E equals V over D. Yeah. Oh no, I know this. You didn't know this. I knew this. What's the V for this one? 500. And the D, it's usually kind of small, so the D would maybe be like a centimeter. Something like this. Maybe 2 centimeters. Okay, did you draw this? We can continue. Adnan?
Yes.
Yep. Okay. So the radioactive decay equation says that. Are you listening? What are you doing? The activity is proportional to the number of atoms. meaning the more atoms you have, the more decay that you have. Kind of makes sense. The activity and the number of atoms are always decreasing, so you always have less activity over time and less atoms over time. Therefore, A is a negative. Mathematically, we say that A is equal to minus a constant times n. So the more atoms you have, the more activity you have. And the lambda here is called the decay constant, where lambda is a positive constant. And the minus sign is to remind us that the n is decreasing. This is called the decay equation. Continue? Continue? Okay, do you have this equation? Yeah? So it's a small question I want you to do now for me is I want you to tell me the units of lambda. Have a look at what it is. Not quite.
Yeah. What is the mole?
Oh no. Oh no.
What is the unit for number of moles?
Just number of atoms. Atom number. Number of atoms.
Then PQ per number.
PQ per new atom.
Let's see. Activity is minus lambda n. So lambda is minus a over n. And what's the unit for activity? B equals. And for n is number of atoms. But remember what a B equal is. It's destruction of atoms per second. So the unit is per second. Also called a hertz, yeah. So the unit is per second for the lambda. Please note that. Okay, doke? Continue? Yeah. Right. Here's a small question for you to try again. I tell you that in a radioactive sample, 1 mole of atoms is destroyed, decays into alpha, beta, and gamma radiation in 1 second. What's the activity?
1 multiplied by the decay constant.
Have a think about it. I'll give you a minute, then you can give me the answer.
One second. It's 1 mole.
We need to multiply 1 mole by
That's the first thing to do. Correct.
So it's n equals number.
But that's not what I want. I want the activity.
Yeah. And
Decay constant.
What's the answer for activity? Yeah. And the units? Yes. He's got it. So, the activity is how many atoms are destroyed per second, which is a mole of atoms per second, I said in the question. But that is just, what's it, Avogadro 6.02 times 10 to the 23 per second. So it's just minus 1 Avogadro's number of B equals per second, of B equals. Continue? Yep. Okay. Okay. Okay, so now I'm getting a little bit trickier. Again, I'll give you a minute to do this one. So you have a sample of 10 to the 10 atoms, and 1,000 atoms are destroyed per second. What is the decay constant? So you'll need to use the formula I gave you. Okay. All very different answers. Let's have a look. Right, what formula are you using? You're using A equals minus lambda n. Correct? So what does lambda equal? Minus A over n. And what's the activity here? It's 1,000 equals, and the n is 10 to the 10. So you said this, I think 10 to the minus 7 is the decay constant, and the unit is per second. Yeah. So what's that? 100. Never mind. We'll leave it like that. Nanos. Okay. Continue. Right. Here's another one. Define activity. By using this definition, express A in the form of a derivative. And I'll give you a small example. Remember, force is the rate of change of momentum. This is Newton's second law. So as a derivative, that means force is dp dt. Also, if you use what you remember from ODE lessons in maths, you might be able to get it as well. So just look again at what the definition of activity is, and then tell me what the derivative definition of it would be. Activity equals some derivative.
N the A over T decay constant.
No.
N.
Not even close.
N Y.
No. No.
He's asking me.
But don't. But sure, why do you need to know? What's wrong? What's the definition of activity?
A rate of decay.
Stop. Now, think back to your ODE lesson in maths. The rate of. What does the rate of mean in the ODE lesson? Yeah, derivative. Okay. So continue, Adnan. The rate of what?
A rate at which unstable
Nuclei. Yeah.
Decay.
So it's a time derivative. Yes, and what is on the top?
dN.
Yeah. So the definition of activity as a derivative is the activity is dN dt. That would be as a definition. Activity is the derivative of the number of atoms as it changes. So that's actually important because to find the value of n or A, we can do this using the radioactive decay equation, but this equation doesn't have any time in it, so we need to rewrite it. So we just worked out this, but we also know that A equals minus lambda n. That was given to you a few minutes ago. So if we put these together, we now get this formula. You've seen this before. Where have you seen problems like this?
dN over n equals minus lambda.
dt. Where have you seen that, Ms. Sharif?
Nice.
Yeah. So we integrate, and what do we get here?
N.
Equals minus lambda t plus c. We can put E on both sides, so we get N equals E minus lambda T plus C. So N equals EC, E minus lambda T. What is N at the very beginning? Let's just call the N at the very beginning N0. So when T is 0, N is N0. So we have N0 equals EC, E0. What's E0? 1. So what's EC? N0. So if I put that back in here, we get this formula. The number of nuclei remaining is the number at the beginning times e to the minus lambda t. This is the formula for how many nuclei we have left. But what's nice to know is that...
This is something
No, it is. But what's nice to know is that the formula for the activity has the same form as well. A0 E minus lambda T, likewise. And in fact, you've seen formulas like this in 2 other lessons. What other lessons have you seen them in? No, in physics though. You've seen I equals I0 E minus T over tau. Q equals Q0 E minus T over tau. And V equals V0 E minus T over tau. Yeah. And I think you've seen it somewhere else, maybe? No, maybe not. Okay. So, in other words, this is not a new type of formula in physics. This e to the minus business is not new. So you know what the graph looks like. What would the graph look like for n? Oh no. For this. Not straight line, Sharif. Exponential.
Really?
Really?
But you took the length to make it straight line.
And did I do that here?
No.
So, it's curved at the moment. Yeah. So we have the exponential decay equations. We'll do an example in a moment. Yes, you'll need to write this down.
What is the name? The
Exponential decay equations. Now listen to this. This proof is not in physics, but this could be in maths because it's a good example of a maths engineering ODE question. So it is not a physics question, this is actually a maths question, this proof.
Now we can do it.
In maths? Yeah. Huh? Good.
Do you have this expression in English which says that the math is the mother of the
Yes, but I wonder if we say father.
Yeah, you say mother.
I don't know actually. Don't know if it's mother or father. But we have the same idea. I think more commonly said though is people say maths is the language of science.
Yeah.
It's more common. Okay. Got this? Continue? Yeah. So, next now is some examples which we'll do. We'll do this together, bit by bit. So if you can just write down the info, and then we'll do each one together. So it's iodine 134, its mass is 268 grams, its molar mass is 134 grams, initially, so initially means A0. A0 is minus 1.32 times 10 to the 20. And I know it's minus because I say it's decay.
So the A0 is 1.
Minus 1.32 times 10 to the 20.
So we care about the sign.
We just need to be careful. Ready? We'll do the first part together because we can do this in our head. How many moles of iodine are there in the sample?
How many moles?
You know, have a look. Give me a number.
268 over 134.
Give me a number. No, do not use your calculator.
2 over 3.
No.
2 times
1 over 2.
0.5.
What?
1 over 2.5.
No. Guys, you're being a bit stupid right now. Please.
M is 4.2.
No, stop giving me a formula. Just give me a number, a single number.
M
No, so
268 over 134.
all right.
268.
A single number.
Yeah.
2 grams.
You're so close. Yeah, but not 2 grams. 2
More.
moles. Okay? You have 268 grams of iodine, and a mole of iodine is 134 grams. Therefore, you have 2 moles of iodine. Yes? Okay, so write that answer down for part A. Got that? Fantastic. Right. How many atoms of iodine are there initially?
2 multiplied by.
So that would be 12.06 times 10 to the 23, isn't it? Okay. We'll just say roughly 12 to make it a bit easier for me. Well, no, I have supposed to have my calculator. So let's have a look at part C. Part C is the decay constant. So the decay constant is minus A over N. Now, do we know the N? We do, you just worked it out. What did you say the N was? It was 2, 12. Is Avogadro's number 6.03 or 6.02? Oh, okay, 022. So this is 12.044 times 10 to the 23. And the activity at the beginning is minus this. So minus is a plus. So that is 1.32 times 10 to the 20. So if I just hit that in, I'll get 1.096 times 10 to the minus 4 per second. Okay, can you write that down, please? Continue. Great. How many moles of iodine are left after 1 hour? So we need to use our formula. N equals N0 E minus lambda T, which will equal 12.044 times 10 to the 23 times E minus 1.096 times 10 to the minus 4, and the time here will be 3,600. Yeah. So let's just hit that in. E power.
This one?
Yeah. Yeah. And I don't know.
That's
I'm
so
waiting all the time that he was going, where is your cat?
Alright. The answer here is 8.12 times 10 to the 23. Got that? Part E. What's the activity? Well, that's nice and easy because activity is equal to minus lambda n, which will be minus 1.096 times 10 to the minus 4 times n, which is 8.12 times 10 to the 23. Eight point nine 10 to the 19. F. How long until there's only 100 grams of iodine left? Now the nice thing here is, I gave you a formula for N and for A, but I didn't give you a formula for M. Want to have a guess at what it is?
N equals M over 1, we change the number.
How can you change the entity?
Well, look, no, it's not too far away. If you want to do it that way, what does N represent? Number of moles. So what happens if I multiply both sides by Avogadro's number? Or not even that. I'll make it even easier. What letter do you use for molar mass in chemistry? MR. So what happens if I multiply both sides by MR? The mass. Correct. So the mass is equal to the mass at the beginning, E minus lambda T. Same formula. So how much do I want? I want 100 grams. And how much do I have at the beginning? 238. Right? No. 268. E minus lambda.
1.096.
Huh, sorry?
The decay 1.
Oh, what is it? 1.096 times 10 to the minus 3, minus 4? Minus 4. And we're looking for the time here. Yes?
The gram?
Yeah.
268 gram.
Yeah. Which is, because I'm using kilograms. Sneaky like that. 268 grams is 0.268 kilograms. Yeah, you know that. And I know that. That's what you're asking me for. Can we solve this? Right. 0.100 divided by 0.268 is 0.3731. So 0.3731 equals e to all of this. What will I do next to cancel the e? Log, cancel, and then divide to get the t. So if I log my answer and divide that by 1.096 times 10 to the minus 4, I lost my minus here, so this is a positive actually. This is seconds. 2.5 hours. What? No.
No, because we were thinking about it. I mean the whole question.
No.
The answer seems big.
Yeah. 2 hours.
For one.
To reduce from 268 grams to 100 grams takes 2.5 hours. It depends on your perspective. Some materials would take 5,000 years to do this, and some materials would take a few seconds. It did. This will be considered a quick decay by most standards. Okay, please write that one down. Got that? Okay. Oh, sorry. Yes. Yes. Okay. How long until the sample is 1/4 as active than it was initially? Okay, so we want the activity to decrease by to 1/4. So what was the activity at the beginning? We worked it out, A0. It was given to us actually.
Yeah, 1.32 to the power
22. And we want to know 20? Are you sure? Okay. And we want to know when will the activity be 1/4 of this? Yeah, or like this, yeah? So if we use the formula A equals A0 E minus lambda T, you can kind of see, well, this is the same thing as 1/4 A0, right? Yeah, so you can just say 1/4 A0. You want to know when will it equal A0, E minus lambda T. So we can cancel the A0s, and we can say log 1/4, when will it equal minus lambda T. So the T will be log 1/4 over minus lambda, which is minus 1.096 times 10 to the minus 4. Yes.
How did you compare the A to A0?
Here, this is 1/4 of A0. This is A0. This is 1/4 of A0. So I wrote this.
Then you wrote A equal A0.
This is the formula.
Yes.
I changed A into this.
Well, how
Because A equals a quarter A0, like we said a minute ago. I said it right there.
A equals 1/4 A0.
Yeah.
1/4 A0 equals A.
Because the question is, when is the activity a quarter of the initial activity? Is it okay? I don't know if it really is okay. Is it okay?
Not understandable. Right.
No, it is understandable. It's just you have to think about it. And I know you don't like to think. I know you don't like to think. You hate thinking about things.
Why do you think that?
Because as soon as you don't understand something and you don't want to think about it, you ask me about it straight away. It's good to think about things. You agree or disagree? You disagree. You like answers now.
Yeah, it's cool.
I know, but in real life, when you go to university, you need to think about things and wonder and consider. 12,648 seconds is the answer here for time, which is about 3.5 hours. So you're a good student, Sharif. You come on time, you do your homework, you do your coursework, but you have one weakness. You do like to think about things. This is your biggest weakness. But the good news is you only have one weakness. Some students have many weaknesses. Nobody's perfect. True. Okay. Continue.
No.
Do you smoke?
No.
Good, okay. That's not a weakness then. Continue?
Smoking is like coffee. What's the difference?
Yeah, but coffee won't kill you. Smoking will.
Yeah.
So, it is like coffee in a different way, a very important different way, if you ask me. Do you have this?
Yeah.
Yep, okay.
Can you go back to the lesson? On Wikipedia?
Geiger Mueller counter.
And what is the first question?
I don't know, because I just go to Google Images and type in what I want.
Yeah. This is for the image.
For the images only, yeah. Because it's not right for me to put the image in the slide and pretend it's mine. I'm just acknowledging that I didn't make the picture, I got it from Google. Yeah. Some teachers don't care about this stuff, but, it's important that you know I didn't sit down one evening and drew that picture of the Geiger counter. I got it from somewhere, It's different for a class. You see, I know you talk about referencing in EAP. So in a classroom situation, when a teacher is using something on the board, it's enough really just to say, I got this picture from this website. But if you're writing an essay for other people to read, that's your work, your sort of publication, then you have to be more formal with your reference, because some people could use your work for their work, and so it has to be clear where the knowledge is coming from. But I'm only using this picture for explanation in class, so I don't need to give a full reference. I can just say this is where I got it from. Huh? In my opinion, it's enough for a teaching context. Yeah. Okay, let's try these questions now. A lot like the example I just did. You can practice with your new Casio calculator.
No, for the exam.
Okay.
I want you to teach me how to.
Okay. Well, start these now, please. Do you want me to keep them on the screen?
Yeah.
Yeah, let me just close the video though.